In the previous lecture, we introduced random variables, probability mass functions, and expectations. In this lecture, we continue with the development of various concepts associated with random variables. There will be three main parts. In the first part, we defined the variance of a random variable and calculated for some of our familiar random variables. Basically, the variance is a quantity that measures the amount of spread, or the dispersion, of a probability mass function. In some sense, it quantifies the amount of randomness that is present. Together with the expected value, the variance summarizes crisply some of the qualitative properties of a probability mass function. In the second part, we discuss conditioning. Every probabilistic concept or result has a conditional counterpart, and this is true for probability mass functions, expectations, and variances. We define these conditional counterparts and then develop the total expectation theorem. This is a powerful tool that extends our familiar total probability theorem and allows us to divide and conquer when we calculate expectations. We then take the opportunity to dive deeper into the properties of geometric random variables and use a trick based on the total expectation theorem to calculate their mean. In the last part, we show how to describe probabilistically the relation between multiple random variables. This is done through a so-called joint probability mass function. We take the occasion to generalize the expected value rule and establish a further linearity property of expectations. We finally illustrate the power of these tools through the calculation of the expected value of a binomial random variable.